Hi everybody, in this video we will talk about quantum numbers and orbitals. But first, let's ask ourselves one question. Why doesn't the electron just fall into the nucleus? So we can think of this in terms of potential energy and in terms of the law of conservation of energy. So let me just give you a very simple physics example that you might have heard of. So let's just say that you're on top of a slide and you want to slide down. At the top, you have no kinetic energy because you're not moving, but you have a high potential energy since you're above the ground. And in very simple terms, potential energy is just energy that is stored when you are attracted to something, but you're not actually touching the thing. So, for example, if you're attracted to the Earth because there's a gravitational force that's pulling you toward the Earth, then, pretend this is the Earth, then you have a potential energy, since potential energy comes from the fact that you're attracted to something, but you're not actually touching the thing. So, now let's go back to the example. As the kid slides down, the potential energy will be converted into some kinetic or moving energy plus heat. So at the bottom of the slide, the kid will be moving very fast. And that's the law of conservation of energy at play. And let's take a look at one note. The total energy is equal to the kinetic energy plus the potential energy. And now that we have that note, let's read the explanation for why the electron doesn't just fall into the nucleus. So let me erase this red earth and let's read the explanation. As the electron gets closer to the proton, it loses electrical potential energy. Now, electric potential energy is just like gravitational potential energy, but instead of the force being gravity that's attracting the person to the Earth, this time it's an electrostatic force that exists because this is negatively charged because it's an electron, and the nucleus is positively charged. So, as the electron falls closer and closer toward the nucleus, it is losing distance, and as a result, it is losing electrical potential energy. But, according to the law of conservation of energy, some of this electrical potential energy is turned into heat and also kinetic energy. So as it gets closer, the electric potential energy will decrease, but that lost energy will be turned into kinetic energy. So the electron, as it gets closer, will move faster, and it will move so fast that it will be constantly orbiting the nucleus, but will never actually fall in. You can think of an electron as a satellite in space that is moving fast enough to not actually crash into Earth. So here's the Earth, and here's the satellite, and the satellite is constantly being dragged toward the Earth, and it wants to crash into it. But it's moving so fast that while it's crashing into it, it's moving in this direction, and as a result, it will, never fall into the Earth, and instead just orbit it. And that's how satellites and electrons work. So now let's go over some terminology. Heisenberg uncertainty principle. This tells us that you can only find the position of an electron or its speed, but not both, unfortunately. And there is an explanation for this, and I'll try my best to explain it. So, when you're observing an electron that's super duper duper small, you have to first shine some light onto it to see it in the first place. Because remember, what we see in the form of light is what is reflected off of the thing. So we have to shine something on the electron, and the electron has to reflect it back. But by observing this electron and, shining light on it, we know the position of the electron. But by shining the light on it, you are giving the electron a little amount of energy, and this energy is enough to change the direction or even the speed of the electron. So by just observing the position of the electron, you basically just change its speed. So that's why you can only find the position of an electron or its speed, but not both of them at the same time. And now it's also really hard to pinpoint the exact location of an electron since it continually changes very fast. Therefore, we use Schrodinger's atomic model, which describes the orbitals or areas in space where the electron is most likely to be found. And in this image, we have a few orbitals. So for example, the 1s orbital, where the 1 is the principal energy level we discussed in the previous video, and s is called the sublevel, which describes the type of orbital it is. So in this case, a 1s orbital just looks like a sphere. And a fun fact about orbitals is that each orbital can have at most 2 electrons. So that will be very important in the future, but for now, don't really worry about it. And here is a graph that shows the probability density function for where an electron might be found in an orbital. So I'm not sure what orbital this is, but this is telling us that at a certain radius r from the nucleus of the atom, the electron is most likely to be found there since its probability density, denoted by this trident squared or psi squared, and it just tells us that this is radius where you are most likely to find an electron in this particular orbital, and we'll discuss this in a future video, so don't worry too much about the probability density function. Just worry about what orbitals are for now. Now let's talk about the types of orbitals we can have. So these are known as sublevels, and it just describes the type of orbital. So we have 4 types of orbitals: the s orbital, which look like spheres, p orbitals, which look like dumbbells, d orbitals, and f orbitals, which have very complex shapes. So if we look at an image of these orbitals, we see that for the s sublevel, there is only one type of orbital, and for the p sublevel, you can see there are 3 types of orbitals, and they include the px orbital, the pz orbital, and the py orbital. And they look like dumbbells, and these dumbbells are lined up on the x-axis, which is why it's called the px orbital, and so on. So the s orbital looks like a sphere. And for the d sublevel, there are 5 types of orbitals, and for the f sublevel, there are 7 types of orbitals, and you can see these shapes are really complex. So I would just focus on the s and p sublevel, because the s sublevel just consists of spheres, and the p sublevel consists of dumbbells lined up on different axes in a 3D graph. And let's look back at this drawing here. So notice how there are 1s orbitals, 2s orbitals, and so on. So the number that you add in front tells you the principal energy level of that orbital, and it tells you essentially how energetic that orbital is. So for a principal energy level of n equals 1, we only have 1s orbital, and this can carry at most 2 electrons because one orbital can carry 2 electrons at most. So for n equals 1, it can have at most 2 electrons. Now let's take a look at n equals 2. At n equals 2, we can have 1 2s orbital and 3 2p orbitals, since if you remember, the p sublevel contains a total of 3 orbitals. So that's why there are 3 2p orbitals. And if we have 1 2s orbital and 3 2p orbitals, don't you think that the total number of electrons they can carry at most is 8? Because 4 times 2 is 8? Well, yeah. What about for n equals 3? If n equals 3, you can have 1 3s orbital, 3 3p orbitals, and 5 3d orbitals. And this is because for the d sublevel, there can be 5 types of orbitals for that, and there are only 1 of each of them. So there are 5 3d orbitals, and 3 3p orbitals, and 1 3s orbital, and 5 plus 3 plus 1 is 9, and 9 orbitals in total times 2 is 18 electrons in total. So the 3 as our principal energy level can hold at most 18 electrons. Now, what if our principal energy level is 4? How many electrons could n equals 4 hold? Well, you could have 1 4s orbital, 3 4p orbitals, 5 4d orbitals, and 7 4f orbitals, and that makes a total of 32 electrons. And notice how if n equals 4, 4 must start off every orbital before putting, the sublevel after it. So for n equals 5 and onward, it's the exact same thing as for n equals 4, except the principal energy level is written there, and it's different for every energy level. So notice how starting at n equals 1, as you go up by 1, you add an extra type of sublevel. So for example, from n equals 1 to n equals 2, we added 3 2p orbitals, and then from here we added 5 3d orbitals, from here 7 4f orbitals, and it just stops there. So you have to remember the types of orbitals that can be found per energy level, and this is meant to be memorized. And an easy way to memorize this is just that from n equals 1 to n equals 4, an extra type of sublevel is added. And yeah, let's go back to this image. Notice how the 2s orbital, which is this giant sphere, and this 1s orbital are both spheres, but this is a 2 and this is a 1, and the 2 tells us that it has a higher energy state, so that is why the orbital is larger, since electrons with higher energy levels can go farther away from the electron. So now that we know that, let's take a look at something called the 4 quantum numbers. So the 4 quantum numbers are just numbers that describe an electron, and the first quantum number is the principal energy level. So this is our very first number. So we're going to have 4 numbers in total, and our first number is going to be the principal energy level, n. This describes the energy level of the electron. It ranges from 1 to infinity, and they are all whole numbers. But you tend to just see numbers from 1 through 7, and probably no more than that. Now, our second quantum number is known as the sublevel. The sublevel describes the type of orbital the electron is in. So it could be a sphere, a dumbbell, or whatever it is. And L can be a maximum, that's not right. L can be a maximum of n minus 1. So for example, for n equals 3, L can be a max of 2. And what am I talking about? Well, let me show you something down here. So the L tells us the type of sublevel. So if L equals 0, then it's an s orbital. And if L equals 1, it's the p orbital. If L equals 2, then it's a d orbital. And if L equals 3, then it's an f orbital. So this is saying that L can be a maximum of n minus 1. So if the principal energy level is 3, then L can be a max of 3 minus 1, or 2. So L can be either 0, 1, or 2. In other words, the sublevels that n equals 3 can have are 0, 1, and 2, which correspond to S, P, and D. And this matches what we learned in the previous slide, where we said that for n equals 3, we can only have S, P, and D orbitals, and that fits the theory that L can be a maximum of n minus 1. Now let's look at the third quantum number, orbital. The orbital ML, with, the L is a subscript, and ML tells us which orbital the electron is exactly in, because if you remember, we have many types of orbitals, so we want to know which one it's in exactly. So we use the third quantum number to do that. So there's a way to write out electrons. For example, for the s sublevel, we know that there is only one orbital in the s sublevel, so it has one line and it can hold a maximum of 2 electrons, and each arrow represents an electron. So there are 2 arrows, so there are 2 electrons. for the p sublevel, the p sublevel has 3 orbitals, so we draw 3 lines, and each orbital can hold 2 electrons, so we draw an up hook, down hook, up hook, down hook, up hook, and down hook to represent the 6 electrons that the 3 orbitals are holding. And this goes on. And the thing about number 3 for the third quantum number is that in order to find out what this number is, we simply have to look at the orbital, order them up, and line them up with 0 being in the middle. So, for example, for the d orbitals, the middle orbital will be 0, and to the left will be -1, -2, to the right will be 1 and 2. So, if I'm talking about this electron, then I know that that electron is in the orbital denoted by 1. So, the third quantum number, or ml, will be 1 for this particular electron that I circled. Now, let's talk about the fourth quantum number. This is called the electron spin. It's which way the electron is spinning. So, if the arrow goes up, then it's clockwise. If the arrow is pointing down, then it's counterclockwise. And the up arrow is equal to +1/2, and the down arrow is equal to -1/2. So for that electron that I circled previously, this was a down arrow, and down arrows are -1/2. So in this case, the ms, which stands for the electron spin, will be -1/2. Now I know the letters are overlapping, but I'm sure you'll be able to see it. Now we are going to do more practice with quantum numbers in the future, so don't worry if you're confused, because I was confused at first too, but you know, everyone gets used to it eventually if you take the time to practice. So let's look at just one example. So let's just say that this is a 2p sublevel, and remember the 2p sublevel has 3 orbitals in it, as we described in the picture, since the p sublevel has 3 types of orbitals, so that's why there are 3 lines. And I drew all the electrons in, so apparently in this 2p sublevel there are a total of 5 electrons, and I circled that one electron yellow, and I want you to find the 4 quantum numbers for it. Well, I already wrote it down, but I'll show you how I got those. So, since this electron's located in a 2p sublevel, then, you know, it will have the first quantum number as 2, since 2 represents the principal energy level, and the principal energy level is our first quantum number. Now, the second number describes the sublevel that we're in. The sublevel that we're in is the p sublevel, and if you remember, p corresponds to 1, so this will be equal to 1, and that's why our second quantum number will be 1. Now, our third quantum number comes from which orbital exactly it came from. So remember, the p orbitals have 3, so there are 3 p orbitals in the p sublevel, and we number it like a number line, so this will be 0 in the middle, and 1 will be on the right, and -1 will be on the left. And looking at this, it seems like this electron's in the 0 category because it's right in the middle, so the third quantum number will be 0. Now the fourth quantum number tells us if the electron is spinning clockwise, which is +1/2, or counterclockwise, which is -1/2. And since the arrow is pointing down, then it's going to be counterclockwise, and it's going to be -1/2. Because remember, if it's pointing up, then it's +1/2, and that represents clockwise, and counterclockwise is a down arrow, which represents -1/2. So, since it's pointing down, it's going to be -1/2. And that's a very brief introduction to quantum numbers, and that's essentially it for this video, and have a nice day.